In the last module, we discussed about the heat transfer coefficients, what is the typical descriptors and so on. In this module, we will discuss about how to design heat sinks and what are the nuances in the design, and we do a first order model and we try to explain it in a simpler fashion and also try to come up with a design rule of thumb to come up with a quick and fast heatsink design for parallel plate heatsinks at least. So, looking at the slide, the heatsinks are typically, the flow arrangement is quite complex in many situations in an electronic systems. One, you can see that there is a heatsink is placed in a duct. The dashed red line shows that the duct, that is the duct cross section, and the heatsink is placed in such a way that there is no air to flow over it or by the side, and all the air or liquid is forced to go through in between the fins. And this typical situation is called heat sinks without any clearance. And in terms of hydraulic resistance, one can write as pressure inlet minus pressure outlet is represented by some sort of a resistance, flow resistance offered by the heat sink itself. When you end up having a tip clearance, this is the so called much more complex arrangement than this, which is a very simple arrangement. If you allow some amount of space on the top, which is very common in electronics, because when you put a PCB and you're mounting heat sinks and lots of other components, a multi-layered stack, that always tolerance issue pops up, and so one always leaves some amount of gap on the top of the fin to the top cover. There is always a certain amount of gap. So if you leave that gap too much, then there is a lot of bypass flow. But one has to leave that gap because during manufacturing tolerance issues may pop up. So there is always typically some amount of gap on the order of a millimeter or so is always left, and that is the case described here. Again, the red dash line is the cross section, and the top one there is some amount of tip clearance. So when you have this bypass, this is the so called bypass effect, where some amount of, if I draw a resistance network here, the flow will go from left to right, because it can, some flow will go only to the top, because flow will always take least resistive path. So the flow will bypass the heat sink and it will go there. So the efficiency or effectiveness of the heat sink goes down, or the efficacy of the heat sink goes down because of this bypass effect. And this is the case where we call it heat sinks with tip clearance. And the last one is the so called the bypass case, where the airflow can go to the side, to the top, and this is much complex situation, and designing heat sinks in that case is extremely challenging and often resorted to more or less computational models, because there will be influence from upstream sources, upstream obstructions, upstream components in the PCB as well. So we will focus on the simple arrangement for this lecture, and to give you an idea, if what is plotted here is heatsink thermal resistance, which is temperature at the bottom of the heatsink minus the ambient temperature divided by the power dissipated by the heatsink itself. That is the heatsink thermal resistance plotted against number of fins. This is fin 1, 2, 3, 4, 5, 6, so on. So if you look the top curve, the bottom curve, it is the case of this situation where there is no bypass. Without flow bypass, what you are seeing is that the heat sink, as you increase the number of fins, the resistance keeps going down. We want to achieve as low a thermal resistance as feasible. So as you can see that in the as you add more number of fins, the thermal resistance goes down. At some point it starts to go up, back up. We will discuss why it is going back up, but this is for a constant pressure drop situation, that the pressure drop across the heat sink, that is P inlet minus P outlet, is kept constant to a certain value. As you can see that with and without bypass, when you have bypass, the thermal resistance, the minima is shifted up. That means the performance of the heat sink is worse than the performance of the heatsink without a bypass, and also the number of fins you are putting is also reduced. This is only the tip clearance that is discussed here, but if you add the side bypass, it gets even worse. So in designing optimization, in optimizing a heatsink, there are a number of parameters for which one designs a heatsink. Is it for fixed pressure drop? In this case, where you have side bypass and the top bypass, you typically design for fixed pressure drop basis, that if I want to improve the performance of a heatsink, I need to ensure the pressure drop across the heatsink is kept the same, so that if I change the geometry or something, it does not grossly affect my flow performance, that is flow going through the heatsink itself. So it is not, sometimes it may not be the pumping power of the fan that is always the metric, sometimes it is the pressure drop, even though it doesn't have a direct energy metric to it. So one always operates when you have these complex situations. The optimization for fixed pressure drop, or should it be fixed pumping power, will be decided based on the flow configuration that is being handled. In this case, this plot shown here, what is shown is without bypass is done for a constant pressure drop, and that's where we are comparing. What happens is that initially when we put fins, the fins typically for a fixed pressure drop, initially when the fins are far apart, then there is a lot more flow going through those fins. But as you add more and more, so as airflow is going increasing, is higher, that means what it says is there are two parts to it. The amount of heat that the fin can transfer convectively to the flowing air is one part, and the second part is the part where how much air can carry, how much amount of energy or heat air can carry from. So those are the two competing cases. One is when you add, initially the fins are far apart, the airflow rate is much higher because of lesser pressure drop offered when. So in this case we are talking about fixed pressure drop, that means mass flow rate is very, very high. So one is improving, we are improving the heat carrying capacity of air is also much higher because we are flowing a lot more air. But as you start to add more fins, the convective heat transfer area is increasing. At the same time, it is also affecting the pressure drop. In this case, fixed pressure drop means it is reducing the mass flow rate. As we go from left to right, the mass flow rate is also reducing, and it keeps reducing like this. It keeps going down. But at a point is reached when you add more than that number of fins, the mass flow rate is so small that even though the fins can deliver more power to the airstream cannot pick up that the heat carrying capacity of the airstream is reduced or it's choked. So that causes the thermal resistance to rise again, and that is the case for both these situations. So what we are going to do is that we can focus only on this heat sinks without tip clearance, and as an example we'll discuss there are a number of types of heat sinks that are available in the market. We are going to focus on what is called longitudinal fins because those are the workhorse in the industry. Most of the electronics you see these parallel plate heat sinks often used because of their simpler construction, lower cost, and also the performance per cost is extremely good for parallel plate heat sink. Even though there are so many other enhancement schemes, still in industry, not in academic research, but in industry, cost is a much bigger player. So the parallel plate heat sinks are typically used. You could have the heat sinks can be classified as longitudinal fin heat sinks, parallel plate heat sinks, active heat sinks. Active heat sinks means there are fans that are blowing air across that heat sink. Then you could have finned foam heat sinks. There are foam open cell metal foams that are available commercially in the market, and there are fins, and then you put the foam so that the fins carry the heat and deliver it to the foams, because the foam has very thinner strands. So the fin efficiency of thinner strands ends up being very poor because of very high heat transfer coefficient in the pore scale of these foams. And then there are heat pipes. Heat pipes are liquid vapor devices where the phase change from liquid to vapor carries heat from location A to B. It is a better thermal conductor, or heat pipes are typically used as a means to transport heat from a location A to location B due to phase change phenomena. We won't get into the details of heat pipes, but these heat pipes are typically placed very close to the heat source. The heat is spread or carried from this. In this case, for example, in the picture shown here, there are these the 1, 2, 3, 4 heat pipes, and this is where the heat is generated. The heat is delivered from this point to this place, and where the air is flowing, and there are lots of parallel plate fins, and the vapor that is liquid to vapor that is happening, the vapor gets condensed, and the condensed vapor returns back to this heat pipe, to this heat source itself, by natural capillary action and also by gravity in some cases. So there could be offset fins, there are offset heat sinks, fin heat sinks, pin fin heat sinks, and they are shown here. These are strip fins, offset strip fin, pin fin, fan heat sink combination. This is the so-called parallel plate fins, sometimes referred as zipper fins. These are some much enhanced heat transfer geometries where there are honeycombs with slots, foams, periodic foams. These are so-called triply periodic minimal surfaces, Schwartz structures, finned foam, finned periodic foam. So there are many different types of heat sinks, and I'm sure you have seen dimpled fins. There are so many. This is a very classical area where many people strive to improve heat transfer coefficient, the so-called enhancement heat transfer, and we won't get to look into all the types of enhancement schemes that exist, but instead we'll look into how heat sinks are classified much. It could be in the laminar regime. The heat sinks can be operated only in the laminar regime or in the turbulence flow regime. It could be steady state, unsteady, internal, external, periodic. There are so many ways to classify these heat sinks. One of the important things is that if you have a pin fin type heat sinks, then there is flow over the heat sink always triggers a lot of instabilities, wake effects, and if you have a fin, in the case of strip fin effects, there is a fin here, another fin here. We are looking at from the top view. As you can see, these are the so-called what is called self-sustained unsteadiness. So there is an interesting enhancement scheme where you want to not operate in the turbulent flow regime because of Reynolds analogy. What ends up in turbulent regime is that if you increase heat transfer concomitantly, the pressure drop or the skin friction also, or the pressure drop increases as well simultaneously. So you don't get enhanced heat transfer, you just get the same amount of heat transfer increase as the same increase in pressure drop. So instead of in the laminar flow there are some restrictions. So instead there have been some studies, and lots of studies in fact, where people try to operate in the so-called unsteady laminar flow regime, where we maintain unsteadiness in the flow by purely means of using certain geometries. And strip fin is one such geometry. Is that what you are seeing here is the top view, and there is a fin strip here, another strip here. As the flow exits this, there is a vortex shedding, and this vortex starts to influence the flow, that is core flow, that is happening here. And you can see here there is a water dye flow visualization at Reynolds number defined here of 750. As you put a dye, a brown dye, there is not much of a change. This is very much a laminar flow. And as you increase from 750 to 1000, now you start to see these vortex shedding from the first strip influencing the second one, and then the second one influencing the third and fourth, and eventually at around 1800 the flow becomes quite unsteady and also turbulent. This itself is a unsteady flow, and people have observed extremely high heat transfer enhancements, that is on the order of 3 to 4 times compared to a laminar flow enhancement. We won't get into it. So as I said, we'll discuss about first a very simple model for pressure drops for heat sinks is obtained by using the so-called correlations that exist. And so in a pressure drop situation for a heat sink, if we want to predict a pressure drop, there are two main contributors. One is the core pressure, that is pressure drop due to flow between the fins, that is called the pressure drop, core pressure drop. And then there are losses because the flow comes from a larger duct and gets contracted to a smaller duct between the fins. So that is the so-called contraction pressure drop, and this typically happens at the inlet of the heat sink, and at the outlet a smaller duct expands to a larger duct, that is the expansion pressure drop. So those expansion losses are to be accounted for. The expansion and contraction, the core pressure drop, the flow through between fins can be described by using this apparent friction factor for a developing flow, Reynolds number based on the this is the inverse of the Grade's number, and half rho v square. For F apparent friction factor times the Reynolds number based on the aerodynamic Grade's number, inverse Grade's number, times half rho v square. And the pressure loss is typically referred based on the contraction loss coefficient and the expansion loss coefficient at the exit of the heat sink times the half rho v square, the dynamic head. And this apparent friction factor is given for a developing flow using this correlation. X plus is again the x divided by the inverse of the Grade's number, and it is described here, the length divided by hydraulic diameter times the Reynolds number. So this loss coefficients again can be, WC is given as the spacing between the channels, TF is the thickness of the fin, and these are coming from Case and London and a few other authors, and these are well known and well established, and so we just use these numbers to predict pressure drop across heat sink, and typically these predictions are quite good, within 10% of the actual measurement, as long as it is in the laminar flow regime. And it is quite commonly used in industry as a first order and possibly one of the easier way to, and many softwares which are called flow network modeling softwares typically use these type of correlations to predict these pressure drop across these heat sinks. And in terms of parallel plate heat sinks, again the typical definition for thermal resistance of a heat sink is defined as the base temperature of the heat sink minus air inlet temperature divided by the power dissipated by the heat sink. There are so many models, thermal models, that are typically used to describe thermal resistance of the heat sink. The first one is the so-called convective resistance model, where typically what is used is 1 divided by the heat transfer coefficient times area, effective area, that is the surface fin efficiency is accounted for. And this model works only when the fins are far apart. When the fins are spaced far apart, that's when these models work. Otherwise they do not work well, and in fact they may actually give wrong idea that as you keep increasing flow rate, heat transfer coefficient keeps going up, so you keep getting better and better thermal resistance. So because they do not account for what this model does is that it only accounts for how much heat is transferred from the surface to air, but it does not account for how much heat can be carried by the air that is flowing across or flowing through the heat sinks. That is, the sensible heat rise, the caloric rise of air is not accounted for in these so-called convective heat sink models. So that causes an issue, and that is the typical problem in these convective resistance model, is that they work well for single fin, but for multiple fins only when the fins are far apart, and we will discuss this little later as well. And there are many correlations for these type of convective heat transfer models, and one of the common ones is the so-called composite solution, where they use a combination of fully developed flow and a developing flow correlation and obtain a composite correlation to describe the heat transfer coefficient in this. So The second one that is sometimes used is the so called fluid resistance, where one describes heat transfer coefficient as 1 by HA effective plus 1 by mCp. M is the mass flow rate and Cp is the specific heat capacity of the fluid. Thermodynamically, 1 by m dot Cp is not a resistance, because m dot Cp times delta T, which is outlet temperature, mean temperature, minus inlet temperature, which is also a mean temperature, is equal to the power. It is the effect, it is not the cause. So, it is actually not driving the heat transfer. The thermal resistance is written the way it is written is based on what is the numerator is the driving voltage difference, or in our case it is the temperature driving force. What is the maximum temperature, what is the minimum temperature? In our case, the base is the maximum temperature where heat source is mounted, and the inlet is the coldest point in the system. So, that is the maximum temperature driving force divided by the power that is dissipated. Power is like a current. So, with this we can describe, but when you do Q equal to m dot Cp delta T, where m dot is your mass flow rate, Cp is your specific heat capacity, and delta T is the mean temperature rise, is only the effect of how much heat you are adding to the fluid stream. So, what is the increase in the fluid stream temperature? It does not describe any potential for heat transfer, it is just because of heat transfer to the fluid how much the temperature is rising. So, if one uses this as a model, this typically ends up being wrong. The only situation where this is correct is that if you treat the mean temperature of the entire heat sink to be the same, which does not make sense either, because only if the mean temperature or increase in mean temperature of the fluid from inlet is very small, on the order of 1 degree C or less than a degree C, then this model will work. Otherwise, this is just a completely wrong model to describe heat sinks. Then there are LMTD based correlations. There are many ways to write these things, and these correlations are given for reference. This is for a simultaneously developing flow, that is the hydrodynamic boundary layer is also developing, as well as the thermal boundary layer is also developing. And one of the best way to describe heat transfer coefficient or the thermal resistance of a heat sink is using our well established classical heat exchanger theory. In a heat exchanger, typically what we talk about is there is a fluid stream that is going in one direction, and there is another fluid stream going in the other direction if it is a counterflow arrangement and it is separated by a wall. And this is the so called counterflow heat sink model or heat exchanger model that is often well described in many of the textbooks that we talk about. And we can use the development from the counterflow heat exchanger model for modeling heat sinks much more accurately. And in fact, they based on experimental data and others that we have obtained and elsewhere, we show that that is a very good descriptor for modeling heat sinks, and one fetches extremely good results within about 10 to 15% accuracy compared to experimental data. So, in a typical heat exchanger, counterflow heat exchanger, we define the effectiveness of the heat exchanger as how much amount the actual heat transfer rate divided by the maximum heat transfer rate that is feasible within the heat exchange arrangement. And the actual heat transfer rate is nothing but what is the caloric conductance, or the MCP, the mass flow rate. Cp is the specific heat of in a counterflow heat exchanger, the hot side fluid times hot side in minus hot side out. Similarly, the actual rate can be also be defined based on MCP of the cold stream into 2 T cold out, the temperature of the colder stream minus temperature of the colder stream inlet temperature. Now, defining, we know from heat exchanger theory that for obtaining the maximum possible heat transfer, one has to use between the two streams, that is the MCP hot versus MCP, the caloric conductance of the two streams. The minimum is the one that is the governing parameter. So, using that, if we describe C min, that is the minimum of the two MCP hot and MCP cold, gives fetches and times the T hot in minus T cold in gives the maximum, versus the numerator can be written in terms of hot, the actual either on the hot stream based or cold stream based. This is the typical definition of a heat exchanger theory, and we can adopt this to a heat sink. The way we do it is that if you imagine a heat sink, there are very highly, the metal part where the fins are there can be treated as one stream, while the air stream can be treated as the second stream. The metal part, because if you were to draw a temperature profile for the metal part, the metal temperature rise is typically very small, on the order of 3 to 4 degree or 5 degrees C. But on the other hand, for the air stream, the typical high performance heat sinks undergoes a temperature rise of almost 30 degrees C. So, when you compare a 30 degree rise versus a small increase of 2 to 5 degree rise in a solid part, then one can imagine that the solid side can be treated as if it was isothermal. That means it has very high conductance, the caloric conductance is very high. On the other hand, the C min is always going to be the air side. With that assumption, this is equivalent to counterflow heat exchangers, where we say that one stream is undergoing phase change where it is being maintained at a constant temperature, versus the other stream where it is undergoing a lot of change in temperature due to sensible heating. So, with that idea, we can simplify this formulation for heat sinks, and that is what we will cover in the next module that we follow.